No, no.
No, you know what it meant.
Yeah. Not see my oh, I just saw it. That
Enter does not work.
oh, there you go.
Hey,
Yes, can you guys hear me there now? All right. All right, so when I talk about paleointensity physics, I'm not going to be talking about the basics of basics, but I'm going to be talking about more of a micromagnetic perspective. How do we model it? How we try to make it as physically closer to the reality as possible with limitations because it's a model. So it's never going to be exactly the same. And then I'm going to talk about the MicroPi method, which is this attempt of getting individual paleointensity for individual sources within a given sample. So, oh, no, it's not. Okay, so we know very well as earth scientists that we have magma or lava, this cools down, it generates magnetic minerals. And the beautiful and philosophical thing about thermoremanent is that, everything is a very, random state, and then you get the energy decreasing, and then basically temperature decreases, magnetic energy increases, and then you get some sort of alignment of all the particles in the direction of the magnetic field, which is a lie. So it's much more complicated than that, and that's exactly why data is what it is. And I'm going to be talking about why that's complicated. So the classic way of obtaining absolute paleointensities of igneous rocks, you just take a macroscopic sample, you measure the remnants in a rock magnetometer, you hit the sample in a given temperature threshold in a zero field, cool the sample, measure the remnants, put it back, but now in the same temperature in the presence of a magnetic field, cool the sample again, measure the remnants. And then if everything works beautifully well, you're going to get something like this, this very linear array plot in which you can use the slope between the TRM gain and the natural remnants lost to basically infer what was the ancient magnetic field. But in reality, it's much more complicated than that because we have so many assumptions for this to be truth. So first of all, we usually assume single domain assemblages, which can also be a problem, as Brendan's going to be talking about this later. But we also need to have the law of reciprocity. So basically blocking and unblocking temperatures have to be the same. We need to have basically the law of additivity, which says that the sum of all the partial TRMs are going to be added and then is going to be in one successive interval, and that each of these PTRMs are individually independent and not interfering with each other. So there are so many assumptions for this. And of course, what happens in reality is something like this, right? We see this weird plot with like not any, so in green you have the best fit with the linear, part of the plot. And then in red you have for the whole thing. And then you can see all the zigzags and weird behaviors. And why does that happen? Because, well, TRM is a much more complex phenomenon than, what I showed in that philosophical representation. So it depends on several aspects. Well, first of all, the mineralogy. Different magnetic minerals are going to have different properties, so the way that they acquire magnetization is different. The cooling ratio, how fast your sample is cooling, and the field intensity, which is going to generate the bias, and then the intensity of, and the how big that bias is going to be depends on the intensity of the magnetic field. And of course, the interactions which we modelers hate. And of course, when you're talking about mineralogy, chemical composition and crystalline structure is going to be affecting basically the magnetic properties. Particle size is going to, and particle size and particle shapes are going to be controlling the domain state. And especially when we talk about soft ferrimagnetic minerals, we have this, peculiar state where we call the vortex state, where we have basically the magnetization along the core of these structures. And then we can actually have multi-vortex state in larger micrometric particles that are going to have a very, very small remnants. They can still be very, very stable, by the way, but they can have like a very, very small remnants compared to single vortex, which can be actually half of the saturation of magnetite, for example. So the thing about vortex state particles is that we now have kind of like an understanding that most of the natural record related to igneous rocks is related to vortex state particles, because single domain particles are just a tiny, tiny fraction, to the general behavior that we actually see. So if you take these particles with the vortex state, and then you run, several micromagnetic models, you can have different energies for different models. Basically, we are achieving local energy minimum states, and each of the states are possible states for those particles, but they have different energies. And not only different energies, but also different directions. And then you ask yourself, which of these states is actually going to be assumed by that particles? Because we need to know that to actually calculate the TRMs. We need to know the properties of it. And the problem is, at one specific temperature, we can get that, reasonably well if we get distribution, a Boltzmann distribution, and calculate what's the probability of one stating appearing. But the problem is, for many of the vortex state particles, we can have domains. So the same particle can have, for example, in this scenario, I'm showing that it could have 3 domain states with different magnetizations and the same energy related to them through the entire range of temperature. So basically what that means, when you look at the probability of them occurring in here from 0 to 1, so 1, it will definitely occur, and 0, it will not. There is a constant swapping between these states across the whole range of temperatures. And what does that mean is that if you heat these particles, so if you're doing thermodemagnetization or basically paleointensity, they're going to fail miserably. So they're going to be changing domain states every time you heating the sample, which basically will cause most of the paleointensity failures that we observe in rock. So it's actually not very surprising to see that most absolute paleointensity experiments fail, because this is a rather common phenomenon when at least when we're modeling, we see this domain state dependence on temperature and the swapping between domain states with increasing or decreasing the temperatures. So probably this particle will fail any thermo experiments. So when we're thinking about modeling TRM, and we want to know oh, these are very important particles within the rocks, how do we, and they're so complex, how do we actually account for all of these domain states? How do we account for cooling ratios? How can we actually predict what would be a TRM for these particles? So we basically have to solve a linear differential equation system that we have something called the transition matrix, which is dependent of temperature functions that we can just tweak around depending on the kind of rock that we're looking at. So if you're looking at, faster cooling, we would use one equation. If you look at more long diffusional coolings, we can use all the equations. And then we have the probability of each state that I've shown happening in a different period of time. So we start running models. So we run hundreds and thousands of models to get basically a sense of all the possible domain states that these particles can have. Then we needed to decrease the dimensionality of that. As Richard said, there's many ways of doing that. You can use PCA to define which are the states that have similar energy. So you can kind of infer that it could be very similar domain states, and you're going to have some domain states that are going to be stable, some will not be stable. So we run a bunch of models to see all the possibilities you have, and then you get those models that they're representative of the whole picture. So after doing that, we have to calculate energy barriers between each one of the models. So I have model A, model B, what's the energy barrier to go from model A to model B? And then we can build these matrices which basically describe the energy barrier between each one of the models, and also the Zeeman field, which is the energy barrier given by the external field right here. What that means is that we can basically simulate and construct any TRMs of any kinds, as long as we have patience enough to run models forever. And in that condition, we can basically try to understand how vortex state particles behave. What would we expect from an assemblage of vortex state particles cooling under a given field intensity and direction and in a given cooling ratio? So there is potential and there is mathematics and physics to do that within the limitation of the models, of course. This is just to show the other possibilities. But one interesting thing is that when you take vortex state particles, single vortex particles, for example, that show this kind of like multiplicity of domain states, and we simulate what would happen to them if you hit them and actually do a classical Thelier, you can see failures in most of them, because as I mentioned before, it's a very common phenomenon with the most naturally occurring particles in nature within igneous rocks, terrestrial igneous rocks. So the problem here is some of these grains can actually behave well, but most of them will behave poorly. So the problem here is heating. So heating will change how the relationship between thermal and magnetic energy are basically fighting against each other. And then if you hit a sample to a given threshold, one domain state can just change to the other. So basically, what would be brilliant was to have an absolute paleointensity method that doesn't require heating. And that's the dream, isn't it? And I am one of the people that took the chance of trying to do that and hope really, really that I won't fail miserably. But, you know, just let's see how it goes in the next years. But so that's what we're trying to do. So one thing that, you know, is very well known is the pseudo-38 method that doesn't require heating. So what you do is you basically measure the remnants, you stepwise AF demagnetize your sample, and then you basically acquire an ARM within the same steps, and then you have a pseudo-array plot, and you can basically, through a calibration factor, correct that into an expected absolute paleointensity. And there are some experimental and empirical tries to way to correct that. Leonard has been working over there for like quite a period of time. And we have really good relationships. So in here, you see the slope produced by this set of samples. And then here you see the relationship between that slope, the paleointensity, and the paleointensity actually measured by all of the other methods that actually required some sort of heating to acquire absolute paleointensity. So there is a very good calibration, of course, but this is empirical. It's like determined by one set of samples. And the question here is, how do we actually go beyond that? How can we try to infer a calibration factor that is more representative of the physics happening between the relationships of like how a TRM and an ARM of a given particle assemblage correlate to each other. And to do that, we go micro. So in here, like as Richard and as Frank, I am a bit of a micro lover. And the idea behind the MicroPi project is that we could pair magnetic microscopy, nanotomography, and micromagnetic modeling to answer to all of those questions. So we start with samples, and then in here, I'm going to show some results of ceramics. So they are archaeological materials. And the reason why we've chosen the ceramics, because we know the magnetic field that they acquired like a couple of hundred of years ago. So we know, you know, if the paleointensity is actually telling us, you know, the actual intensity, or if we've, I don't know, maybe we could have like a weird magnetic field like in the, you know, Ediacaran or the Devonian. So instead of avoiding all of that and trying a new method, we're choosing something that we know the magnetic field, which magnetic field it acquired. So we do QDM analysis. So we just measure the magnetization in a thin section that we prepare from those samples. We choose a region with like sources. We cut a sample. We take that sample to the synchrotron or to whatever tomography technique that you have. You scan it, segment it through several different ways, as Richard has shown a few here today. And you micromagnetic model it, and then you get the properties to answer all these questions. So the idea is that we could try to get the slope, so the relationship between ARM and TRM from the QDM measurements, and we could try to get the calibration factor from the micromagnetic modeling. So going to some results, the samples that we have chosen to try this at first, they are archaeological materials from the Jesuitic missions in Brazil. They have relatively reversal thermomagnetic curves and a response that indicates pretty much stable recorders. But most importantly, they have these beautiful results, both indicating the same paleointensity. So we've chosen them because, we're trying a different method. We need like good samples to know if what we're doing is right or if we're far and how far we are. So from that, we go to the magnetic data acquisition, which Frank explained a lot how it works. So basically, we have a thin section of that. We have step-wise AF demagnetized and measured the demagnetization of the entire thin section in a rapid system. Then at each step, we take the sample out of the rapid system and measure it in the QDM. So we're doing measurements in both equipment at the same time, so we can actually compare our inversions to each one of the steps to see how far away we are. Then we do the same thing with ARM acquisition. So you acquire the ARM, the same steps, both reading the magnetization in the rapid system and in the QDM in 2 areas. We just picked 2 areas because why? Because of time. We didn't have enough time in the QDM, so we could only do 2 areas. And then, I'm going to explain this later, we do an IRM acquisition. So we apply a pulse of like 2.7 Tesla to one direction and 0.1 Tesla to the opposite direction. And the idea behind this is to do a coercivity filter for the anomalies that we are observing. And then, of course, we measure it. So going with the results, with how do we process the data? And this is interesting because, as Frank said, this is a brand new area. So there are many people trying different approaches and trying to really find out what's the best way of getting to meaningful results. So to detect the sources in the surface, meaning the anomalies, we use an automatic source detection that Gelson has developed, which basically calculates the total gradient of the anomaly on the surface. It tweaks with like the contrast of these anomalies and calculates the log of the Gaussian and then tries to identify where each anomaly is. So what all of these filters do is to basically detect automatically where all of the anomalies you see on the surface are. And the reason you do that is because when you're going to inverse, instead of actually manually picking all of them, you just do it automatically for all of them. And of course, you can always cross-check if you have like overlapping of windows and this sort of things. But the interesting thing here is that we get to use those same windows for all of the data sets. So when we're doing like AF demagnetization or ARM acquisition, we see how each one of these different and individual anomalies are evolving, or like how they're demagnetizing over time. And the way we do that is because, as Frank also mentioned, QDM also takes a LED image from the same field of view that he's taken. So this is the LED image related to this QDM measurement right here. So we use this LED we take one LED and we call it like the referencing system. So we use this referencing system to align the other LED images of all of the other measurements we do. And we do that basically by calculating something called the affine transformation matrix, which you basically given in 2 points. It detects, how these 2 points correlate to each other. And then we can calculate a correction matrix to align one image to the other. And the nice thing about it is that, as the magnetic fields are changing, the LED images are the same. So you can just take that transformation matrix and you can take a map that's not aligned, apply the correction matrix, and then you're going to have all of the maps in your system aligned to the same coordinates. So that means you can really verify individually each anomaly and do things more automatically. So there are many ways of inverting the magnetic signal. Like, so you've seen an anomaly on the surface. What we really want is what's the magnetic moment that relates to that anomaly. Frank showed one way, which is calculating. So basically, the source location from tomography, and then you can use spherical harmonics to try to calculate what's the anomaly and try to invert the magnetic signal from that. We take a different approach in which we firstly sort all of the windows, all of the anomalies by the intensity. So the ones that are like strongest, the ones that are weakest. Then we run the source position detection, which is an Euler deconvolution algorithm. So basically what it does is just from the signal you've seen on the surface, calculate the position of the source that's generating that anomaly on the surface. So it's also a linear inversion. And with that position of the source and the reading of the magnetic component, the Z component on the surface, we can use a linear inversion to infer the magnetic moment. So the step forward in this paper that is actually under review now is that we use this linear inversion to then calculate a nonlinear model. So we're trying to refine what the linear model was, which is just an initial approximation. And then we do that first for the strong sources, strong windows. So we invert them, so we know the magnetization. We forward it to this to one height, which where when the thin section is. We remove the strong windows, and in that way we can see the weak signals much more efficiently. And just for an example of how this works, this is not a ceramics, as you can see, this is basalt. And it's a very highly densely packed with like many anomalies. And you look at that like, oh my God, how do I make sense of what is an anomaly here and what's not? And the beauty of using not your eyes, but mathematics and physics is that you can let the algorithm detect them by you. And then you decide if they actually anomaly or not by just cross-checking, basically. So in this plot, we show basically some results of this method that we're using. And then you can see the stars, which is the star right here in both stereo nets. So first of all, this is the first paper Gelson published, which was just the linear approximation. And this is the second one that is on the review that uses the linear approximation to actually get a calibration for the nonlinear inversion. The star that appears right there is the actual remanence measured for the whole thin section in the rapid system. And as you can see by the color right here, when you start adding together all of the anomalies that it has detected inverted, when you reach like a few thousands of anomalies, we are almost perfectly reproducing the results that we are seeing for the whole thin section. So that gives us some piece of confidence that our code is working because we're cross-checking with the rapid system that we are measuring. And that's also interesting. Let me just go back here for a second, because you can see that with just a few thousands of anomalies, we are reproducing the signal that we are observing in the rapid system. And that's important because last year, actually this year, I've published a paper with many people that are here and also collaborated with me. They're trying to calculate how many particles you need to actually acquire a meaningful TRM, within the direction of the magnetic field. And within that predictions, as you can see here for triaxial, spherical, oblate, and prolate grains, just a few thousands of them seems to be enough to actually acquire TRM that's actually closer to the magnetic field. That, of course, will depend on the strength of the magnetic field as well. If you have like a very, very weak field, the bias is going to be lower, meaning they're going to need more particles. But as you can see, the results that I'm showing here are also kind of like a confirmation of what we have calculated earlier this year, that you don't need millions of particles to actually get a meaningful result. And then you're going to ask me, but Alison, what about the non-dipolar signals that we see on the surface? They are non-dipolar signals. Don't they matter? Because, they exist. So what we've done is like I've taken this thin sections to basically CM microscopy. And what you can see is that for all of the cases, these are associated with large multi-domain, most likely particles. So this is one example. This is another example. You can see right here, it's colored by, you see the iron oxides right here, and then you can see the scale here, which is about 50 microns. So these are pretty big particles. Just another example and another example just to make a point. But that's important because we have different ways of inverting the magnetic moment, and we have ways that consider octopolar, quadrupolar components, and only dipolar components. So then you ask, what do we do with this, non-dipolar anomalies on the surface? So to try to tackle that, I have run models because that's what I do. And I have taken data from a previously published paper that we've acquired tomography from samples from the new Proterozoic carbonates, and then we've identified all of these magnetic particles within that, run micromagnetic solutions, and got the most likely domain states for each one of them. So from that micromagnetic solutions, we have, is it going to go forward? Or it doesn't want to go forward. Oh, yeah. So for each of these particles, we start from the micromagnetic solution, and then I have calculated the stray field. So basically, the magnetic field that is leaking from the particle at different heights. So we're going all the way from 10 nanometers to 30 microns away. The idea here is to see how these particles, how the magnetic field of these particles change with, with a factor of distance. So in here you have, like, for example, this 750 nanometer particle with complex magnetic structure. And then you here that have the stray field 20 nanometers away, which looks very non-dipolar. But then a micron away is already very dipolar. So in order to understand how dipolar things were or not, we are developing a Cartesian method of inverting dipolar, quadrupolar, and octopolar components, just using punctual sources as well. And what you can see here in blue, in the box plots in blue, the dipolar component inversion only does behave really badly if you're like maybe 0.5 microns away from the source. So you can see in blue right there, the box plots related to like all of the models that we run and the R-square, which is basically the measuring how the variance is explained by that model. For just the dipole sources up to like 0.5 microns, it can't really explain all of the anomaly you're seeing. But then, and then in orange, you see when you fit the whole multipolar component, so dipolar, quadrupolar, octopolar, it explains much better at like closer distances. But when you're like nearly a micron away, they are nearly indistinguishable, meaning that a dipolar component by itself can explain the anomaly really well. And that's just an explanation for what you see in the spot right here. So we have particles with different maximum elongations from 300 nanometer, from 30 nanometers all the way to 1.2 microns. And then you can see in the y-axis here, the angular misfit between our predictions of the inversions of the magnetic moments and the actual position of that, the actual value of that magnetic moment. In that corner over there, in that figure over there, you're seeing just the dipolar component of the multipolar fit. And right here, you're seeing only using the dipolar component. And yes, of course, closer to the particle up to like a micron or so, if you're using a multipolar component fit to adjust and to invert a magnetic moment, is going to behave much better. But a micron or 2 microns away, you can basically explain it really well. And that's just using the dipolar component of a multipolar fit. So what I mean is the dipolar component by itself, if you're not really close to your particle, is enough to explain most of the anomalies that we observe. So that's just a justification for why we use just a dipolar fit and not a multipolar fit to the whole thing. So if we're looking at something at the surface, it looks non-dipolar, it's probably going to be large multi-domain particles or clusters of larger particles. Because when you put like tiny single domain or single vortex state particles together and in a small cluster and you're far away, it's going to be looking like a dipole as well. Oh, yeah. So sorry, I just mentioned this is the angular misfit. So just the position that we were inverting compared to the actual real direction. And this is the misfit in magnitude, which is also important. So as I said, it's justifiable using a dipole fitting safeguarded by the anomalies with good fitting only. So you're not going to put, our approach is not to use all of our inversions, but we're always looking at the quality of the inversion of each of the window. If the window has a poor inversion, like a poor R-square, we just chopped it away. We don't look at that because there are many problems already to be accounting for than putting like bad inversion results in your data. So now we invert the magnetic moment for all of the windows across all of the data sets. So for AF demagnetization, ARM acquisition, and IRM as well. And we only get the windows. So first what we do is only get the windows that the IRM to one direction is greater than 0.9. And why is that? Because when you apply a magnetic field, you're going to give like a really strong remanence to all those particles. And then you can see that, so in that stereo plot right there, you see that the IRM that we have applied 2.7 Tesla with R square greater than 0.9. And here to the opposite side, 0.1 millitesla. And then when you just leave those with like the R square greater than 0.9, and you say, oh, we can actually apply coercivity filter here. I don't want anything that didn't flip. So if I have something that has like more than 150 millitesla of coercivity, it's going to behave poorly when I'm actually doing the pseudo-Thelier. So I'm just going to chop it off. So when you do that, you can just remove all of the windows that have like a bare R square fitting, that have high coercivities, and you have a much, much smaller data set, but more constrained to work with. So these are the two maps that we have. From all of these two maps, we've run all of this filtering, which is automatic, by the way. So you just define these parameters and then you run your models. And in here, you can see the different results that we got from the sample. And in the red triangle is basically the combined magnetic moments of all of the anomalies that we have inverted. And in the yellow star is basically the Fisherian mean of all of that. What basically means that the Fisherian mean is going to be considered unit vectors. And the in red, when you get this component, we're actually considering the magnitude of the magnetization that we have inverted. So in one, we're only considering basically the directions, and the other one, I'm considering just then as unit vectors and taking the direction that we have inverted. And this, for the NRMs, the result of the book that we have measured for the whole thin section. So we perfectly reproduce it. And actually, when we look in this map right here on the on that side, that's the AF stepwise demagnetization of 176 sources, so less than 200 sources, going from the NRM to 100 millitesla. And right here is for the whole thin section in a rapid system. So we're confident enough that we are reproducing these results well for this sample, of course. And then now we go to the actual comparison. Right here we have for the whole thin section, so measuring the whole thin section, AF demagnetization, ARM excision, and on the other side, the results of our inversions as well. So the points right there are the actual result of the inversion. The curve is the best fit with the alpha 95, assuming a student T distribution, just to calculate, how the errors, how well that fitted model can explain the data. And when you plot, and when you plot right here, the pseudo-Thelier for the whole thin section, we get a slope of minus 1.62. And when we look at the micromagnetic from the QDM measurements, and then we see just for the linear fit right there, we have a slope of minus 1.3. So very comparable, not still the same thing. But actually, if we use the same interval or a very closer interval that we use in this case right here, or just taking the samples right there where we have like a better confidence in the fitted results, we can actually get a better result. And then it goes to minus 1.6. But at the same time, it's like, this is just a way of showing you that if we can get more data, we can improve this. And then we don't have to actually think about, oh, do I fit the whole thing? Do I fit like, part of it? But the thing is, this is already, in our opinion, at least one first good approximation of what we're seeing for the whole thing section. So what do we do now? We have the slope. It's what we need for individual sources. Now we have to decide if those sources are good magnetic recorders or if they're not. So we go to actually the micromagnetic modeling to try to calculate the calibration factors. So we've taken several areas within our QDM system, with our QDM measurements, and we have performed different types of tomography. We have performed flip slice and view, which has stopped showing the video here now for some reason. But we're also doing now is, so I have this data already. I have segmented it, I didn't put it here because it would be like a much longer talk than it already is. And but I'm running the TRM models and they take a while to run. But we're also doing this, or the fancy tomographic method called tachographic tomography that I thought Richard is going to be talking about, but he didn't. But basically, I was actually counting it. That's why I didn't explain it here. Sorry. But we're doing some synchrotron time to do this tomographic technique to get the actual picture of how these magnetic recorders are and actually see their position within depth to see if our inversion is estimating basically where they are just by looking at magnetization is actually working or not. And in here you have just one example of how it works. Basically, you just put the X-rays with a bunch of like diffraction patterns, and then you can invert real images, segment those real images into real morphologies, and then you can get like nice models like this one, where this is for basically a speleo theme. It's not reproducible, unfortunately. Anyway, you're just gonna have to trust me. There's a nice model where we can basically identify the magnetic minerals within that tomography. We can model their magnetic properties, get the remanences, get to know if they're stable, if they're not. And then when we're looking at the inversions we did, we can then go back and say, oh, this anomaly right here is associated to a grain that we're not very sure stable. So we can either chop it off or keep it in the data set. And the nice thing about it is that we're also going to apply it now that we know that we at least are getting the inversions within the QDM sort of like right to rocks from a plutonic system in Brazil that people from Liverpool are also working on, to trying to get the idea about the moment of the weak magnetic field in the Cambrian, and seeing it with using a micromagnetic model to predict the paleointensity. We can actually get like high resolution paleointensity for this critical periods of time. But it's also interesting highlighting the possibilities of using this for extraterrestrial samples. We have the example of Mars, which we expected at some point lost its atmosphere because it lost its magnetic field. So we have lots of questions about it. And also this really nice paper, they're trying to understand like what we can determine from, you know, the history of Mars by looking at just the paleomagnetism of it. And the interesting thing is that Perseverance is collecting samples from Mars right now, and we have cores, and we hope that one day these cores are going to come back and we're going to do paleomag in them. But the thing is, these are very few samples, and wouldn't it be brilliant if we could have paleointensity method that won't have such a high failure rates, because basically of the nature of the particles within that. So the idea is that we can look at this very small sample data sets to get snapshots of the Earth's magnetic field, not requiring heating, just using QDM data and running hundreds of models. And that's just basically because, as I mentioned earlier, we now have an idea that if you have stable recorders, you don't need millions of particles. So in here, you see the number of particles, the field intensity, and the angular misfit, basically how far we are from the actual field direction within the number of particles. And then we see that in most cases, and for most magnetic fields, as long as it's not critically low, we can get that really good TRM resolution with just a few thousands of particles. So I thank you a lot for your patience to listen to this long talk, and also some acknowledgements in here. And thank you.